Alright, so here we begin chapter on the Brownian motion, which will consist of 5 sections. In the first section, we will define Brownian motion and Brownian bridge, and also have some general discussion of stochastic processes. Then in sections 2 and 3, we will give 2 examples of convergence to a Brownian motion and Brownian bridge. So these will be perhaps the main results of this chapter, and they will give us examples of a central limit theorem on the space of continuous functions on 0, 1 and 0, infinity. So you can view this as some sort of infinite dimensional central limit theorem. Then in section 4 we will compute some probabilities of some events of interest for the Brownian motion and Brownian bridge, and as one application we will discuss this Kolmogorov-Smirnov test from statistics, which will combine the convergence result from section 3 with this computation of one of these probabilities. And then in section 5 we'll discuss Skorohod's embedding of a random walk into a Brownian motion, and as one application we will prove the law of the iterated logarithm. Right, so right now let's start with the definition of a stochastic process. So what do we mean by a stochastic process? Right, so the definition of the stochastic process is simply a collection of random variables indexed by some set. Okay, so we consider some probability space omega with sigma algebra F and the probability P on it. Okay, and we consider some set T, which is an index set for our process. Okay, and then a collection of random variables that we will denote xt. So these are just random variables on our probability space with the index coming from the set T, is called a stochastic process indexed by T. Okay, so a stochastic process is basically just a collection of random variables indexed by a set. In this chapter we'll consider examples where the set T will be some subset of a real line, like an interval 0, 1 or half line from 0 to infinity. But the most basic example that you can imagine of a stochastic process is, let's say, taking some random variable and then building a function of t out of it. So you can take, for example, cosine tx, where you index t here will be any real number, right? And x is just some fixed random variable on your probability space, right? You defined a collection of random variables now indexed by t in the real line. So this is an example of a stochastic process. Now, there are different points of view that you can take how you view a stochastic process. So as a result, you can sort of use different notation to emphasize these different points of view. Okay, so for example, the way we define the stochastic process is just a collection of random variables indexed by some index t, right? And a random variable is a function on a probability space, so if you make this dependence on omega in your probability space explicit, you could write it like that. In some cases, our index set itself will have some structure. For example, it will be a metric space, or for example, a subspace of the real line. So the index t itself may be a variable of interest for us, and so you might sometimes be interested to view your process really as a function of both the index and omega on your probability space, right? So then you can view it as a function on the product space, and you can write x as a function of both t and omega in this form. Now, in some cases, you want to think of x really as a function of t, as a function of your index. So in that case, you might emphasize t as a variable. So of course x depends on omega, but if you view it as a function of t, you can write it like this, or in the usual probabilistic convention, if you want to make the dependence on omega implicit, you can even write x of t. But if we want to focus in particular on this last point of view, that you want to think of the process as a function of t, okay, then we can write that this map from omega into the function, so x omega, this is a function of this variable t. Okay, you can also write it like this if you like. It's x as a function of t for a given omega. Okay, so this is just a map from our probability space with a sigma algebra f to a space of functions on t, right? And the space of functions on t is denoted RT, right? So as usual, RT is just a collection of all functions, real valued functions on t. And if we want to view this map as sort of a random element, so we want this map to be a measurable map, then we can consider a sigma algebra on the space of all functions, which we have already seen in chapter 1 when we discussed Kolmogorov's consistency theorem. Right? We can consider what we call the cylindrical sigma algebra on this space. Right? And of course, this choice of cylindrical sigma algebra simply encodes the fact that we consider all xt to be random variables, right? So for example, if we take some finite subset of indices, let's say t1, tn, right, in a subset, finite subset of this index set t, and then we can consider some Borel set B on Rn, or let's say on Rf, which is simply Rn when n is equal to the cardinality of this set F. Right, and then the event that xt1, xtn belongs to this Borel set, well, it's a measurable event, right? It belongs to the sigma algebra F on our probability space, simply because we agreed that these xt are all random variables. But of course, you can also rewrite this event from the point of view of x as a function of t. So you can say these are all omega such that this x omega as a function of t belongs to the following subset on the space of functions here on RT, right? It belongs to B times RT without this finite set F. In other words, you do not put any constraint on the values of xt when t is not in the set F, and when it's in the set F, you force it to be in the set B. This type of sets were called cylinders, and these sets form cylindrical algebra. Okay, so viewing this map as taking values in the space of functions with cylindrical sigma algebra, it's basically just a restatement of this fact that we want to view all random variables, or all xt, as random variables. Okay. Now, when we talk about Brownian motion and Brownian bridge, we'll have some more specific information. So we won't just view them as taking values in the space of all functions. will have some additional constraints, namely the so-called sample continuity. Okay, so let's give a definition. Okay, when we talk about sample continuity, we mean with respect to the index t. So in other words, on our index set t, we want to have some topology, but we'll just restrict ourselves to the case when T is a metric space. Okay, in this chapter, it will be simply a subset of a real line with the usual Euclidean metric. Okay, in this case, we can talk about continuity of this process. So the definition is as follows, that we call a process xt sample continuous if for all omega in our probability space, this function as a function of t, or if you wish, you can denote it x dot omega. So this process, when you view it as a function of t, will be a continuous function on this space. Okay, so that's the definition of this sample continuous process. Now let's give a related definition of a process continuous in probability. So there is a weaker notion of continuity of a process when we say that a process xt is continuous in probability. This just means that as random variables, xs converge to xt in probability, okay, whenever s converges to t in this metric space. Of course, this notion of continuity in probability is weaker because sample continuity implies almost sure convergence of xs to xt. So this, of course, implies continuity in probability. Okay, and so once your process is sample continuous, you have some additional useful properties compared to just a general random function in the space of all functions on T. But before we discuss those, let's go ahead first and construct and define the main processes of interest, namely Brownian motion and Brownian bridge. And our main focus will be first on constructing the Brownian motion. Okay, one can give kind of a short and dry definition of the process, which we'll give a little later, but instead we'll start with a definition which emphasizes several key properties of this Brownian motion right in the definition. Okay, so the definition of the Brownian motion Wt for t greater or equal than 0. Okay, so here the index set will be the half line from 0 to infinity. And first, it's a sample continuous process. And then it should have the following properties. Okay, the first property is that each xt as a random variable is a centered Gaussian. Okay, for all t. Centered, of course, means that it has mean 0. Now, it looks a bit redundant, but the second property here gives a more specific version of the first property, namely that we'll assume that x of t is not just centered Gaussian, but its specific variance t. Then the third property will be that this process is stationary. Okay, so this is called stationary. And what this means is that for any times t and s, let's say t less than s, the increment of the process xs minus xt should have the same distribution as x at the time s minus t. So in other words, this should be Gaussian with a variance s minus t. Okay, so the increment of the process has a distribution that depends only on the increment of the variable s minus t. So the last property is that the increments are independent. Namely, if you take any times t1 up to tn for any n, the increments xt1 minus x0, okay, x0 is 0, so I don't need to subtract anything here. Then the increment between time t2 and t1 and so on, these are independent. Okay, so this property, of course, is called independent increments. So let me just write it down here that we call this independent increments. Now, in number 2, although it looks redundant to mention number 1, sometimes in 2, one only specifies the distribution of this process at time 1. Okay, so if you say x1 has a standard Gaussian distribution, then you can easily derive using properties 3 and 4, then xt must have variance t. So I just put it directly in the definition, but if you start with this as a definition, just specifying time 1, then it's a little bit less redundant. Now, in 4, because the increments are independent, they are jointly Gaussian. So increments are jointly Gaussian. Now, from the increments, just by adding them up, you can, by a linear transformation, of course, obtain your process at those times x tau 1, x tau 2, and so on. And because it's a linear transformation of these independent Gaussian, right, this will also be jointly Gaussian. And if you take 2 times, let's say, s less than or equal than t, you can calculate the covariance of this Gaussian process. The expectation of xs, xt, if you rewrite xt as xs plus the increment, the fact that the increment is independent, so independent of xs, gives you that this is just expectation of xs squared, which is s. And you can write this as a minimum between s and t if you do not want to specify that s is less than or equal than t. Okay, so in particular, this jointly Gaussian distribution of xt1 up to xtn, right? It's just a Gaussian distribution with 0 mean and covariance matrix given by this minimum of ti, tj. And so here, just to save some space, I'll write a minimum between s and t like this. So the covariance matrix is a minimum of ti, tj for I, j from 1 to n. And now you can give this kind of short and dry definition of a Brownian motion if you like. Okay, so you can say that Brownian motion xt for t greater or equal to 0 is a sample continuous centered Gaussian process with covariance given by the minimum between s and t. And In this definition, when we say that a process is Gaussian, we mean that all finite dimensional distributions are Gaussian, right? So here, Gaussian process means that all finite dimensional distributions are Gaussian. Now, of course, the question is whether such process exists. And first of all, just by Kolmogorov extension theorem, a process xt with such finite dimensional distribution does exist. Okay, so let's just mention this first. Right, and this is because in this finite dimensional Gaussian distributions, they are consistent, right? If we add some more indices t to a finite set t1, tn, well, the covariance of a bigger Gaussian vector is consistent with the covariance of the original vector. So the original Gaussian is just a marginal of this Gaussian on a bigger finite dimensional space. So by consistency, such process exists, but the main question here is then sample continuity. And one thing that we should notice right away, that continuity is not automatic once you know finite dimensional distributions, right? So you can have a continuous process and redefine it or just change it slightly without changing the distributions, but you can make it discontinuous, right? So you can think of a very simple example, okay, where you take your probability space to be just 0, 1 with Borel sigma algebra on 0, 1, and the Lebesgue measure as your probability measure, right? And you can take the index set T to be also the interval 0, 1, okay, and with Euclidean metric. And then you can define a process x1 to be just 0 everywhere. And you can define process x2 to be an indicator that t is equal to omega. Now you can see that for any index t, right, if you view this as a random variable as a function of omega, so as a random variable, well, both of these have the same distribution, right? And the distribution is just a Dirac mass at 0, because the indicator for fixed t, indicator that t is equal to omega, right? That happens with probability 0. But x1 is sample continuous here, but x2 is not. So we introduced this indicator that kind of breaks the continuity at one point, and so for every omega it's not continuous. Of course, it looks a bit artificial, but the main point here is that we have to ensure continuity of this Brownian motion. In other words, we have to show that one can construct a continuous version of this process, okay, starting from just a general process xt ensured by Kolmogorov's extension theorem. Okay, so our next result will give one such construction. So we'll show the existence of the Brownian motion by a specific construction. Now, in this construction, we'll need the following simple lemma that I will refer to the notes for the proof. It's a one-line calculation that you have the following estimate for the tail of standard Gaussian distribution. So the tail of standard Gaussian distribution with just the integral from c to infinity for positive c of the standard Gaussian density can be bounded from above by e to the minus c squared over 2. This construction that we'll give basically will show that the Brownian motion exists. Now, it will be enough to restrict ourselves to the interval 0, 1. So we'll just construct Brownian motion xt for t in 0, 1, okay, simply because by the definition of by the property of independent increments, you can simply glue the copies, independent copies of the Brownian motion just by adding them at time 1, right? So you can start at time 1 and add another independent Brownian motion and so on. So it's enough to construct this on the interval 0, 1. Now in the exercises we give another construction, or we outline another construction, the so-called Stochastic construction. Okay, but the kind of proof that we'll give here, in some sense it's more fundamental, because it contains the seed of similar proofs on much more general spaces, you know, on kind of a general metric spaces, whereas Stochastic's construction uses representation using orthogonal series, so it's very specific to, let's say, the interval 0, 1 or the real line. Okay, but the construction that we'll give here, in some sense it's very natural. So if you take the process above, the process ensured by the Kolmogorov's extension theorem, then the main idea here will be to simply look at the values in some dense set and then approximate everything else by the process at those times, and then make sure that along the way you do get the continuous process, right? So the main idea will be the following, that we'll now start constructing this sample continuous version, which we'll rename Z. So we'll call it Z. And the Z will be, of course, just our process xt, whatever it is, for some dense set, and more specifically, we'll choose the dense set to be dyadic numbers. So for t of the form k over 2 to the n, right? So in 0, 1. And then we'll redefine x, or you can say we'll redefine x to this new process zt for other t, okay, by approximation at dyadic times below your t. So by the following approximation procedure. So namely, if you take some t, now it will be convenient here to write this dyadic approximation starting from just a dyadic expansion of this number t. So if you represent this number t using its dyadic expansion, so as this series where each coefficient tj is either 0 or 1, okay, then we'll denote tn to be dyadic of the form k over 2 to the n, which is below your tn, right, the closest one below. So it will be simply a sum up to n, right? So it will be something of this form k over 2 to the n below t. And we'll also agree that t0, so 0th approximation is just 0 for all t. And then we will show that this limit of x at these dyadic approximations from below, it does exist almost surely. So we'll denote this zt, so it exists almost surely, and it's continuous. It will give us a continuous process. So it will be continuous in t with probability 1. And on the event of probability 0, when we cannot control things, well, we'll just redefine it to be, for example, 0, to be some continuous function. that event is 0, so it doesn't really matter to us. And so what we want to show now is that this limit exists and is continuous. Okay, so the way we'll do this is to write this dyadic approximation as a sum of links between different levels of dyadic approximation. So a sum j from 1 to n of these increments x at the level j, so tj minus x, tj minus 1, okay, where we use that x t0 is just x0, which is 0. And the reason why we want to write this as a telescopic series is because these increments will have a very good control over them. So, right, these increments, they will belong to the following set, right? It will belong to the set of all increments of the form xk plus 1 over 2 to the j minus xk over 2 to the j, right, for k from 0 to 2 to the j minus 1, right? And that's because tj and tj minus 1, they can be written as a dyadic with the denominator 2 to the j, and the only difference can be in the numerator, right? The numerator can differ by 1 at most. And the point is that by the lemma that we mentioned above, and by the fact that these increments are Gaussian and their variance of this increment is 1 over 2 to the j, so it gets small very fast with j, gives us a very nice control that will imply the convergence and continuity of that series. More precisely, we can write that the largest among these links here, so the maximum over k of these increments, exceeds 1 over j squared, and we'll see that we have a lot of freedom in the choice, but we choose 1 over j squared just to be a convergent series. Now we can bound this first by removing the maximum just by the union bound. There are 2 to the j of these differences, so we'll just write this is less than 2 to the j times the probability that one of these links exceeds 1 over j squared. Of course, by stationarity, they all have the same distribution, so we can just take the first one. So x 1 over 2 to the j exceeds 1 over j squared. We can then rescale, because we know that the variance of x 1 over 2 to the j is just 1 over 2 to the j, so we can just divide by the square root of that and write it in terms of standard Gaussian. So it will be the same as standard Gaussian, or x1 greater than 2 to the j over 2 divided by j squared. And then we apply the lemma above to bound this Gaussian tail by, well, because we have absolute value, it will be twice e to the minus 1/2 times this constant squared. So this will be 2 to the j divided by j to the 4th. But we can see here clearly that this decreases very fast. Everything is dominated by this 2 to the j in the exponent. So when you sum over all j of this upper bound, you still get a convergent series. And we want this in order to apply the Borel-Cantelli lemma. Okay, namely, by the Borel-Cantelli lemma, the probability that these events happen infinitely often is 0. So in other words, probability that the maximum of the above links between xk plus 1 over 2 to the j minus xk over 2 to the j exceeds 1 over j squared, right? This cannot happen infinitely often, or probability that this happens for infinitely many levels j will be 0. Okay? And now we'll see that that's all we need to conclude that the limit of this dyadic approximation exists and is continuous, right? Because on the complement, so with probability 1, we have the opposite, right? We have that this maximum here is bounded by 1 over j squared. For large j, of course, that also depends on the realization, so depends on your point omega in the probability space. But for omega in this set of probability 1, eventually for large j you will have this control that all these links will be less than 1 over j squared. Of course, this implies that the zt, or the limit of dyadic approximations, which now you can also write as a telescopic series of the increments, this series or this limit exists on this event for such omega, right? Because your links or the elements in this series are bounded in absolute value by 1 over j squared eventually for large j. And then it remains to show continuity, right? That this definition of the process zt is continuous. Well, to show this, if you have 2 times t and s which are close to each other, so let's say they are less than 1 over 2 to the n, right? In particular, this means that if you take a dyadic approximation Tn, which will be something of the form k over 2 to the n, and you take dyadic approximation of S, okay, which will be something of the same form, m over n over 2 to the n, the numerators here cannot differ by more than 1, right? Either they are the same or they differ by 1. Okay, so in particular, they are neighbors, so the difference at those times will be a link at the dyadic level n. And so if you represent the difference of this process at time t and time s just using triangle inequality, okay, so in other words, you relate these limiting values z to their dyadic approximation x at dyadic times tn, then on that event of probability 1, right, for large n, you know that this difference here, which is a link, it will be bounded by 1 over n squared, right, for large n. And then this first term here, well, it's just a tail of that series where each term is controlled by 1 over n squared. So when you add up, so here if you add up these errors, 1 over j squared starting from n, you will get something of the form 1 over n, right? It's still a tail of convergent series, so it will be small for large n, and the same for this last term here. This will be less than 1 over n. Okay, and so as a result, for large n, that depends of course on your point omega in your probability space, this difference will be bounded by, let's say, 3 over n. So this shows the continuity of this process zt on the event of measure 1, and on the set of measure 0, we just define z to be, let's say, 0 on that exceptional set of measure 0. Finally, it remains to just notice that zt still has the finite dimensional distributions that we want. This definition, or redefining the process x by this approximation, what we get, you consider this process at finitely many times, it's still going to be the Gaussian with the covariance that you want, right? That with this covariance of the Brownian motion, right? And this holds because this is true for dyadic, simply because it agrees with the process x. And then for other t, you just apply continuity, right? Though the process x converges to the process t, so the distribution of the process x converges by continuity, or almost sure convergence, to the distribution of z. But on the other hand, when you do that approximation, your process x at dyadic times is this Gaussian, and you simply have to appeal to the fact that the Gaussian distribution, when covariance matrices converge, the Gaussian distributions also converge. So Gaussian distributions are continuous with respect to the covariance matrix. Okay, so we constructed a process with the same finite dimensional distributions, and it's now sample continuous. So it is by definition a Brownian motion. So in other words, we constructed a Brownian motion.